my name is Brittany Griego. I am a senior at the University of New Mexico. My mentor is Dr. Laura Crossi. I am working on a project of a hydrogeochemistry of springs in the Sandia Mountains, New Mexico. Springs are an important water resource for both anthropogenic use and a source and support of ecosystems in the arid Southwest. What we are trying to do is seeing how many springs we have and seeing their hydrogeochemistry. We're looking at the water itself and also looking at the rocks surrounding it. So basically we're looking at the chemistry of both the water and rocks. After we receive the data back from these analyses of both the chemistry of the water and chemistry of the rocks, we then are compiling all of our data sets into a regional database, which is called the Spring Stewardship Database, to preserve valuable information, make the data accessible to others, and provide important baselines for future comparison. The figure shown right on the right here, we see how many springs have been visited during this project. Our methods include both field and laboratory methods. First, in the field, we look at the location and analysis of the spring itself at its source. Then we move into the geologic and geomorphic setting, describing using the springs inventory protocols. And finally, we look at the hydrologic and hydrochemical field parameters using YSI and Oakton meters. We're targeting the pH, total dissolved solids, conductivity, dissolved oxygen, salinity, and temperature. Finally, we then take these analyses back to our laboratory and we perform alkalinity analysis. We then go into stable isotopes with using the Picaro cavity ring down spectroscopy. And we are also looking at the major ions. So IC, we are looking at the major anion solutes in the water, and also the ICP, which is the major cation solutes in the water. So first, here we have our results in discussion. First on our list, we're starting with stable isotopes. On the very far left, we see a schematic of how water can be transported from large bodies of water, such as lakes and oceans, into land areas, and then transported from there through river systems, or we're looking at specifically whether there is a monsoon recharge or a winter recharge. Finally, in our middle graph here, we are looking at the stable isotopes of the Cienega rain collector. We had a woman who had collected samples there, and not only had she collected rain, but she also had some snow samples, which we see on the far left at the bottom. And we know that because they are very negative. All of our samples that have very negative values will fall within the winter recharge area. Now, she also collected some rain samples, which are the purple at the top. Those are very much more amount of oxygen 18 and deuterium found in these waters. Then we see Daklong and Cienega. Both of these samples fall right in the middle between both of these. I had collected both samples from a winter season and also a monsoon season here in the summer and in the winter of the school year. And finally, we're looking on the very far right graph. We looked at Capulin, Las Huertas, and then again Cienega and Daklong. We basically compared those springs to each other. We found that we were off on a little bit of the trend line, which was the local meteoric water line. And unfortunately, we used a smaller scale so that way all of the samples would be projected, and so they're a little bit more level than the other samples are here on the middle graph. Next, we are looking at our results back from the major cation and anions. We see here a fiber diagram here on the very far left. We see that most of our samples contained a lot of chlorine and also sulfates, as well as magnesium, and also our carbonates down there at the bottom right triangle. And this then coincides with the amount of samples that work through the Sandia and Manzano Mountains. There are two different sides. There is a silicate side, which is our granite, and also a limestone side. This would then go into our sodium and chlorine graph, basically to show that most of our samples contained more carbonate minerals, which indicated that they fell within the limestone side of the Sandia Mountains. And there were a couple of silicate weathering, which then indicated that they had moved through the granite side of the Sandia Mountains. And finally, the samples presented in these diagrams include samples taken in years prior. These samples are from 2014 to present, and we had found that there were no significant changes in both major ion or stabilized isotope composition. We did find that a lot of our samples were winter recharge, except those samples that were taken at the rain collector. Those were specific monsoonal recharge. And then the water rock interactions that we found contained a lot of calcium bicarbonate and calcium magnesium chloride sulfate waters, which means that they were more through the water rock interaction on the limestone side. The fault structures played a major role in controlling the spring occurrence. We found that a lot of our springs fell within a fault line. If you go back to my poster here, we see that there is a geologic map that shows both the limestone and granite side, and also the black lines indicate fault lines. And as you could see, a lot of the samples that we had taken near the Sandia crest fell within a fault line system. And finally, we found that there was carbonate dissolution that occurred in the waters since they traveled through the Madeira group. And it also did include some salts. And even though there was not much silicate weathering, there was still some movement through the faults on the silicate side with the Sandia granite group. And here are my references. And I would like to thank New Mexico AMP for funding me through this project, as well as the Cibola National Forest, and also UNM for everybody who I had worked with, such as in Dr. Ali in the Analytical Chemistry Lab, and also the Center for Stable Isotopes with Laura Burkemper and Vera Altoduri. Thank you so much.